from D121 University.
I'm D121 from中海大学。I should be a foundation study at University.
Okay, now the floor will be taken by each team's chairperson to introduce your teammates to the whole group.
Good afternoon, dear judges and fellow competitors. Here 我从建国高中，他也是张雅成、徐仁仲、陈宇俊、戴志荣、梁友仪。
Good afternoon. These guys and these are my teammates. 郑怡琪、吴永琪、郑佑and Ethan.
Hello, honorable judges and fellow competitors. We are taking same period and I'm the captain Ethan. And these are my teammates. Great.
Okay, now the opponent team should challenge the reporter team is your problem.
Challenge problem 6 and its whole tower. Each team should write down your representative's name.
Reporter take control.
Honorable jury, fellow competitors, this is a reporter from Human Celsius, reporting column number 6, tennis ball tower. Build a tower by constructing tennis balls using 3 balls and a single ball on top. Investigate the structural limits of such a tower. How does the situation change with more than 3 balls per each layer and a suitable number of the ball on the top layer are used? We mainly focus on discuss the structural limits and the stability, and to investigate the structures of more than 3 balls per layer. Last, what parameters will influence the stability due to the problem statement? So this is our outline for the report. First, I'll talk about our preliminary experiment about an observation of how we define stable or unstable. And our theory includes the static equilibrium and structural limits. And our equipment parameters, our experiment wants to find the limits and other structures, and discussion about the error of the experiment and different coefficient of friction. Last, the conclusion. So first, we define stable when this structure does not collapse, because it is because the topmost normal force did not give enough friction to the lower pole, so it will cause an unstable situation. And for the static equilibrium, these are the assumptions. First, we assume that it is stacked closely, which means that there is no gap between the poles. Then there is a uniform weight and regular sphere, which means that there is no deformation, which means that it is a rigid body and the structure. And this will be the O1's vertical forces. This part is supporting the weight of the first ball, and this is equal to these vertical forces, M1 sine theta and F1 cos theta, and plus M3 equals to N2, and this is the horizontal forces and the torque of the ball. And we define that this is the maximum of friction coefficient between the balls, and the maximum friction coefficient mu PT, and this is mu PT, and this is the maximum friction coefficient between the table. And because that this is a triangular pyramid, so therefore we can know that the sine theta equals to this and cos theta equals to this. And when we input the sine theta and the cos theta, we can know that N1 equals to 1 out of 3 and N2 equals to 4 out of 3 and this is how F1 and F2 equals. And when we put this would be the boundary condition of this would be the limit of this when we input the N1 and F1 into this formula. And when we look at the structure of three layers, we can see that the O1 still represents as the vertical forces of O1 still looks like this, because it is supported by these 3 normal forces. And so the both 2 vertical force looks like this, and horizontal force looks like this, and this is for the full form. And also, when we input the sine theta and also cos theta, we can know that N1 equals to this, and these these are magnitude of different normal forces and about the frictions. And about the structural limits, when we set that there is n layer, the topple always looks like this. The vertical forces that supports the weight of the topple. And in the middle part, the vertical force looks like this, and the horizontal force looks like this. And the torque 2F and cos phi are equal to this. And the layer part, the bottom part of the n layer, which means that it is contacted to the surface, such as table or different other surface, and it will look like this. And for our experiment equipment, we use a board with non-woven, which is the most similar structure, similar platform that we can find. That the friction coefficient is similar to the tennis ball tower, and the lifting table can change the height and the data, and the 3 tennis ball component. And this is how we measure the coefficient of static friction. So for this part, when the data changes because of the lifting table, so we control that the height and changes the data, we can know that this formula. Thus, we can know that the maximum of friction coefficient of tennis ball in our system is about 0.79. And when we use this measurement method to measure the coefficient of static friction for the table surface, then we can, using the same method, we can know that the table, the friction coefficient of table is about 0.55. In our first experiment, we controlled, these are the control variables, and we changed the friction coefficient of this part, and we want to investigate if it's stable or unstable. And this is the experiment result. We can know that the first, and when it's the second layer, the friction coefficient is about 0.4 to 0.3, and other layers, it equals to 1.3. And for the second experiment about the mass of the top tennis ball, these are control variables, and we still want to investigate about the stable and unstable situation of the tower. And when we are changing when we are changing different platforms and this is the experiment result. And we change the mass of the ball on top by inputting sand or metal balls inside to control that it is still round, so it will not cause deformation by pressing. And when we look like this, you can see that our theory line looks like this. However, we cannot match. The deviation might be caused because that we cannot conduct our experiment as an idle line. So therefore, in our theory, the boundary condition limit is 10 volts of 10 layers will be the maximum boundary condition. And however, it will cause larger deviation when it is about 10 and 9 when the amount of layer increases. It is because that we cannot conduct an experiment as that idolized as our theory, because in reality parts they might cause deviations. About the more structures discussion, we try to investigate the structures of more than 3 volts per layer, and after calculation we can know that 3 volts per layer is stable. After experiment, we can know that 4 volts per layer is unstable, 5 volts per layer is also unstable. And it is because that in this part we consider how more structures effects. And the 4 volts per layer, the data is equals to 45. And the 2 codependent data equals to 2 as equals 1, which means that it is unstable. And 5 volts per layer is the Q mu is larger than 1, which is also unstable. And for about 6 volts per layer, because the interspace is bigger than a volt, so you cannot, it is impossible to build a structure like 3 volts per per layer, like it has hexagonal column. Here are the possible arrows in our experiment. First, the gap between the bolts. After measurement, we can know that when the data is equals or less than 51.5 degrees, the structure will collapse. Conclusion. Compared with the friction between tennis balls and zero, the friction between tennis balls has a greater impact on the structure. And with only one tennis ball at the top, only the structure of the bolts layer can be balanced. And whether there is a ball on the top can affect the balance or collapse of the structure. And this is the end of our presentation.
So thanks for your presentation. I just have several clarifications to make. So you said that in the first part of your presentation, instability is whether you can stack up the tennis ball tower without any falling. Am I correct? So, and in the later part of your presentation, you measure the instability with the amount of layers you can stack. So if I have 3 layers with 3 balls each layer and three layers with 4 balls each layer.
Top layer with 1 ball or 3 balls.
I'm talking about stack a tennis ball tower with 3 balls each layer.
Also
And-
the top layer.
No, top layer only contains 1 ball. How do you compare the stability of these 2 towers with different amounts of balls per layer? Because the height, the layers you can stack are the same.
So we know that after calculations, 4 balls per layer and 5 balls per layer is unstable because the data and the friction coefficient does not support the normal force.
So now your definition for stability is the amount of the friction coefficient. So
No, it means that after calculating, we can know that it is impossible to support, so it will collapse.
okay, but why is this impossible to support?
Because this angle is the data angle is equal to 45, which means that it is just the same as the maximum static friction.
But if you increase the friction coefficient, you will be able to support it.
But we cannot change the medium, so the friction coefficient cannot change.
Okay, can you go to page 21? Is that on 21? The previous one. Okay, I mean, it seems like I'm out of time.
Your comment has really, to compare the
Arthur John from Mr. Miracle, and now we proposing problem 6 tennis ball tower. So the problem statement says that we have to build a tower by stacking tennis balls using 3 balls per layer and a single ball on top. Investigate the structural limits and the stability of such a tower. How does the situation change when more than 3 balls per layer and a suitable number of balls are on the top layer are used? So I think the key questions are the reporter has to define the theoretical limits, and he has to confront that theoretical limit with this experiment, and he also has to define the stability, and also he has to explore the situation for other structures such as the different number of balls. The overview of the report, and the reporter used the free body diagram to calculate the friction. All that is required to support that structure. For their experiment, they changed the roughness of the board. They also used the lifting table, and they used tennis balls throughout all of their experiments. In experiment 1, they controlled the mass in a platform, and they explored how changing the structural limit, changing the structure of a tower changes stability, and varying the number of the balls of each layer. And for experiment 2, they varied the mass of the top ball, and then they measured how many layers they can stack without it falling apart. So the pros and cons, the reporter changed crucial parameters, and they set their assumptions, which is that there are no gaps between the tennis balls, and tennis balls are rigid bodies, they don't deform. But for the cons, they have no vague fitting of experiment. There's no theory confirming the structural limit. Also, there's no verification of the friction between the balls, and they have enough persuasive theory because they do not consider friction information. And there is poor explanation of the graphs. And here are some points I want to discuss. So first, I want to discuss what defines the stability, because in the reporter's report, there were 3 definitions for stability. And also, I want to discuss how the effect of how mass and transformation will affect the structural limit and the stability. And then I will go over the theoretical limits and the real limits, asking the reporters what their view on this is. And then I would like to explore some of the graphs they presented in their presentation. And for the experiments, I would like to provide another way of quantifying the stability. And we would also like to discuss how changing the condition of the balls would affect the stability of such a tower. So I would like to begin my discussion. So, in your theory, does it predict structural limit? For example, for 3 layers, for 3 balls per layer, is there a height limit?
3 balls per layer, and we predict that the structural limits will be 10.
The structural limit will be 10. Why? Where does it say in your theory?
This is a structural limit of the amount of layers.
The structural limit is 10, and that is predicted by your free body diagram.
Which do you mean free body diagram?
The blue dot is your experimental data, and what is the black dot? What does the black line mean?
Be the theoretical, because above to there's no.
Wait, this is the graph of the mass of top balls with the amount of layers you can set. I'm asking you if the mass of all the balls are the same. Is there a structural limit with your theory?
10.
10. But where does it say?
As the graph is not that accurate.
But that is changing the mass of the ball. That's not changing. That is not the layers. That's not the relationship between the stability and the layers.
Then we can't predict.
Okay. On to this point. What defines stability in your experiment? Can you explain one sentence?
I mentioned that you define it as how it lasts or not.
Or not. And I mentioned in my 2-minute question that if there are 2 towers with equal layers but different balls per layer, are their stability the same?
We cannot do the magnitude of the stability.
So your quantification is simply the layers you can stack. Okay. So do you think there's a better way to quantify the stability?
particular, we would like to know what's your problem.
Also, if there are three layers, how stable is it compared to a tower with only 2 layers? They can both stand and they do not collapse, but how stable are they relative to each other?
Or should we consider the normal force that might act between the same layers?
It might act in the same layer. So you're saying that you can quantify the stability by calculating.
Then what do you mean that you have the way to quantify stability?
We think that you can maybe disrupt the system a little bit and see how it reacts. So maybe you could have a table that is actually the oscillator, and maybe you send some vibrations onto the platform. And
Vibration on the platform.
yes, and you can see when the tower collapses to the strength of your vibration.
But the recorder believes that the vibration might cause deviation, and when you cannot predict how it will vibrate or affect the gaps.
Exactly, but the gas is part of the stability too.
But in vibration, it might cause different gaps because we cannot idealize an experiment in this reality situation.
Yes, but you need to see, if you use vibrations, you can actually see how this tower falls apart, and you can quantify its stability. I would think that is a better way to quantify stability instead of calculating your coefficient of friction that is required. You agree with our point of view?
I still believe that vibrating will cause deviation of gap between the modes, and we cannot make sure how it's stable.
All right, we go to page 17. Page 7. No, we go to the page where the you go to a page where it shows the data for the mass and top ball, show these layers can be stacked. Yes. So it shows that for the mass is lower, when the mass and top ball is lower, you can actually stack more layers.
Yes, because the friction, when the normal force is not proportional with the friction when you add up the amount of layers. So in fact, when the normal force increases faster than or bigger than the friction. So when the mass of the top ball is lower, you can.
But doesn't the top ball hold the entire tower together? You showed in your video that if you take off the top ball, the tower collapses. So if this mass approaches 0, what will happen to the tower?
So the reason why I think that the normal force and friction is not proportional is because that when you add different layers, so it means that the normal force given to this flow and friction is larger. Do you agree with that?
Yes.
And so when the friction is not large enough to support the normal force given by our, so it will collapse.
Yes, I understand, but can you go to your graph of the mass top ball? The graph. Yes. But if the mass of the top ball approaches 0, then you wouldn't be able to build the tower at all. So if the mass continues to decrease, then the amount of layers will be able to stack will also decrease.
Yes, I agree with that.
Okay, so what is this red region here and this yellow region?
That should be, this line should be out here, but
Oh, okay.
and it means that it's stable or not. So
Okay.
that means that it's not stable. It will collapse.
It looks like your line goes down horizontally forever here.
No, that's because our theory can only predict that it will go to 10.
Oh,
So
okay.
it only ends at 10.
Okay. And now I would like to move on to deformation. Do you think deformation affects the stability of the system?
We don't think that it will affect that much. However, we still believe that if we have a more proper way, we should consider the deformation inside. But however, we don't.
Because you just said that the normal force affects the stability, but shouldn't normal force affect deformation as well?
Can you rephrase?
I think the normal force affects the deformation, which may affect the stability.
You mean like when it's the formation is caused, it might cause it to be more stable because it is stuck inside the ball.
Yeah, I'm asking you, do you think it's going to make the system more stable or more unstable?
Also, if we change this ball into maybe a really large amount of weight, with real large weight, so it will cause deformation, and this part, so it will cause the structure to be more stable.
You think it will make it more stable?
And we only consider the two layers.
Two layers. And okay. Have you ever considered changing the friction coefficient of the ball?
Yes. We believe that it will affect the yes, it will affect.
Yes, but did you conduct experiments confirming this prediction? For example, when you go to the page where it says that it is impossible to stack tennis tower with 4 balls per layer and 5 balls per layer. Can you go to page 23? Yes, exactly. So if you increase the friction coefficient to match this condition, will you be able to stack tower?
If the friction coefficient is too small, then it will collapse.
Yes, but do you think that if you had more time and you were conduct more experiments, you could confirm that you will be able to stack this?
Okay, so I believe that the friction coefficient of the top as well as an infrared parameter that will affect this a bit.
So
I agree with that.
also, okay, you can change the friction coefficient. And can you go to your free body diagram?
Which page?
Anyone will do. Is there only one solution to the system? Is there only one solution for the static equilibrium?
Yes.
Is there, but what happens if you consider deformation? Do you think there will be more than one solution?
Because when you consider the deformation, there might be multiple contact points that the friction and normal force will act on. So there will be multiple solutions for this. And
So the entire tower falls apart. Because there's only one solution, the entire tower falls apart. If one ball does not satisfy the condition.
if we consider the deformation, it might become an indeterminate problem because we don't have that much function to solve the unknown values.
Okay, thank you. And can you go to the page where you explain how you measure the frictional coefficient? So when the ball is sliding down, does it rotate or
So it slides down.
it doesn't just rotate? So the friction of all the balls are the same.
Yes.
Okay, just have to make sure of that. Do you think the mass of the ball, like if all the masses of the ball are the same, then does that affect the stability?
You mean in this part?
Yeah, you don't just change the mass of the top ball, you change the mass of all the balls.
I believe that it will change the stability because it causes normal force and friction to be different. Yeah, so because when you change the mass of these balls, you mean, is that what you mean?
Yeah, so all that mass influences is the normal force
Also friction.
and also friction.
And friction also changes when normal force changes.
Okay, thank you. Well, that concludes my proposition.
Thank you.
So in our discussion, we discussed the definition of stability, and the reporter agreed with our observation that this definition for stability varies throughout the application, and we provided another way to quantify stability, and that is to introduce some disturbance to the system. And the theoretical limit for presentation is that for 3 balls per layer, they can only stack up to 10 layers. And the effect of the change in the mass of the top ball, according to the reporter, changes the normal force and friction of the lower layers, so that affects the stability. And in our discussion of the deformation, the reporter says that he thinks deformation might cause the system to be more stable, but we did not see any experiment verifying this. So, thank you.
first question is for the recorder. Could you turn to the page with the relation between the layers you were able to build and the mass of the top wall? Not this one. This one. So, as I understand it, you were trying to fit a curve for your data. However, have you noticed that not a single one of your data points is actually on the curve?
Oh,
What is the R squared value of your curve? R squared value. You know what that is? Okay, never mind. So for my next question, I would like to ask, you said you changed the coefficient of friction between the tennis balls. How were you able to do that? Because under my knowledge, the coefficient of friction only has to do with the surface properties of
yeah, we're changing those mediums by different different gradient of this one.
I'm sorry.
Not different gradient. We're changing, for example, we say standard taper and other.
Okay, I understand. So for my next question, you mentioned that when you changed the mass of the top wall, you were able to build a 10-wall tower. As I understand it, in some of the references that I saw, the tallest tower they were able to build was 9 walls. So your feat is actually pretty incredible, and I would like to ask why you didn't include any photographic evidence of this. Okay, never mind. So for my next question, I would like to ask, you mentioned that when you built a tower with 4 balls per layer, it was actually unstable. However, you also mentioned that your stability was based on whether or not the tower collapsed, and you were able to photograph it, meaning that it didn't collapse. So I don't understand the contradiction here.
So if you change the friction coefficient between the tennis ball and when it's large enough,
You mentioned the page with 4 balls per layer.
the 4 balls per layer will not collapse unless if when you're not changing friction coefficient of the tower, the 4 balls will collapse. However, when you're changing friction coefficient like this,
Could you turn to the page of the photo? Yes, that was the previous. This one. You said it's unstable, however, it hasn't collapsed.
In our experiment, we use a hexagonal column to try to fit it. So we put it on top, however, we didn't release our tennis.
Okay, I understand. So for my next question, how was you mentioned that the weight was added to the top wall by adding sand or metal balls?
Yeah.
However, I would like to point out that by doing this, you would probably cause deformation of the ball, which you said yourself that you did not consider.
Yes, but if you consider deformation
Okay, so,
inside of
time
a
to
component,
You are just
by stacking 3 balls per layer and using 1 ball on top. Investigate the structural limits and the stability of such a tower. How does the situation change when more than 3 balls per layer and a suitable number of balls on the top layer are used? Here's my summary of the report. First, the reporter explained the structure composed of multiple balls per layer wouldn't collapse. And for this theory, he used multiple equations to explain static equilibrium. And for his setup, he uses a lifting table to calculate the coefficient of friction, and also obviously tennis balls. And so here are some variables that he changed. For the independent variable, he changed the coefficient of friction by changing the surface of the tennis ball, and also added mass to the ball, to the top ball by adding sand or metal balls into the ball, and also changed the types of structure. And the dependent variable was stable or unstable, which was actually not clearly defined in the reporter's report. So here's a summary and comment of the discussion between the reporter and the opponent. And so the opponent asked, what is the prediction for the maximum number of layers? To which the reporter at first replied that it was 10 layers. However, I believe they misunderstood the opponent's question, because for 10 layers, that was actually changing the mass of the top ball and does not actually answer the question. And also, the opponent asked what the definition for the stability of the tower with 3 balls was, and the reporter answered that stability was defined by whether or not the tower collapsed. However, they also showed a tower that did not collapse, and they explained that it was unstable. So I feel like this is very unclear and should be explained better. Also, the opponent asked, does the normal force also affect the deformation of the structure, which the reporter mentioned that they did not consider. The reporter answered, under the circumstance of 2 layers, it will not be of much significance. And also, the opponent asked, in the stability test, do the balls roll down the slope, or do they just slide? And the reporter answered that they only slid. And so, in my discussion between me and the reporter, I asked why there were no points on the fitting curve that were actually, no data points that were actually on the fitting curve, to which the reporter did not give me a clear answer. And also, I asked how they changed the coefficient of friction, because I did not hear this part clearly, and they answered that they changed the surface material of the balls. And I think this is a pretty good answer to my question. And also, I asked, so here are my comments for the opponent and the reporter. For the reporter, I think they had a large amount of equations, which was really good. However, they had a very incorrect concept of stability, also lack of experimental evidence to support their theories and assumptions. Also, their fitting curve was very problematic, and there was also a lack of photographic evidence to show us what their experiments actually looked like. And for the opponent, I think they pointed out very clearly the flaws in the reporter's report, and also gave clear questions. And finally, for some missed points, I would like to point out that the stability, which was the main point of the problem statement, was not actually discussed very well by the reporter. Thank you.
About the discussions today. First of all, the stable and unstable is defined as collapse or not in our experiment, and the reporter still believes that the method that the component has set, the preparation, may cause the variation of different gaps between the tennis ball changes. So it will not be, it will be unclear structural limits when you use this method to define if it's stable, or you find a number for the magnitude of stable or not, like it's larger. Okay, and when the mass of the bubble is smaller, the more layers it can stack. And the deformation is one of the main causes of deviation, because when we didn't consider the deformation inside, because it would become an indeterminate question when we consider deformation, since you have the multiple contact points. And also, for the reviewer has mentioned that why none of the dots fits on the fitting line, because the theory line. It is because that in reality, experiment we cannot assume it as that idealized, so it will cause the maybe perhaps that the angle of the bottom would change, and also all of the tennis balls are different because it's in a reality situation. So this is why it cannot fit with the fitting on well. And the friction coefficient is the most important of the tower design. When the friction coefficient can reach your boundary, the whole structure, for example, 4 balls per layer, can be stacked. Thank you.
Last time, question possible. Any question?
So, you treat the problem of the spherical ball, the real tennis ball is a groove. So I wonder, the presence of this groove will affect your conclusion, even some spatial limit. I think this is how it's before.
It is one of the parts of the division that might cause in our experiment, but I just believe that because in our theory we assume it as an exactly sphere, so but in reality we should consider about it.
You think you can make the tower more stable, and this can also make the tower more unstable. So for example, if the balls at the bottom are not, the diameter for the groove part is smaller, so the bottom layer is not stacked symmetrically, and the tower may tilt toward a ball that is stacked in the groove, and that will cause the tower to be more unstable. But if all of the grooves are aligned and they all interlock, then they might make the tower more stable.
So I would like to point out that in the reporter's report, they mentioned they basically considered the only friction forces that were to be dry friction. And but I believe that the friction force between tennis balls is not that simple because they have fuzz, and there may be some forces holding them together. So the groove of the ball is actually a very important factor. For example, if you were to lay out, if you were to cut open the tennis ball and lay them down, perhaps you would find that the coefficient of friction actually increased, which suggests that the surface area actually matters, since dry friction is not the only type of friction that is at work in this experiment.
It might cause different contact points when the groove is stacked together, and just like the opponent has said, it may make it to be more stable or unstable because there are multiple contact points, so it will not look as our theory if we consider the grooves.
Any more questions?
Can you just go back to comparison of a series and the extreme there's a curve and they say there's no point matching the curve. Yeah. No, just a simple question. So your y-axis method of
It's kilograms.
what's the unit? I don't really understand. Huh?
Kilograms. Like we fill the ball of the top layer with different kilograms of sand or metal balls inside and change the mass of the top mass.
Okay. So this should be the top layer, right?
Yes.
At the top layer. So have you checked, because I think the statement X, you should try more than 3 balls per layer, and maybe some kind of Super Bowl number of balls on the top layer, right? With maybe spatial arrangement. So it kind of like you only try 1 ball on the top layer, right?
Yes.
Okay, I got it.
More questions?
Question for 3 things. In this problem, it was asked to consider a 3-dimensional arrangement. But if I simplify the problem into a 2-dimensional context, how do you describe this? Just put everything like this, stack it up.
You mean imagine it as a platform, 2D platform. Then
Still with gravity.
so we could only consider it as two energies. So this cube will support the weight. Inside of 1 out of 3, it would become 1 out of 2. Also, these would, are these still 3 layers, or you assume that as 1 or 2?
I'm asking, for example, you just stack up 2, 1, 2, 1, 2, 1. Will it be more stable or more unstable?
I believe that will be more
is stacked like a pyramid, it will be more stable than the three-dimensional one. But if it is stacked like 1, 2, 1, 2, 1, 2, it will be more unstable.
I believe it would be more stable since on one view, like a slight jostling would cause the entire thing to collapse.
Nice job, sir. Ready? Short points for the reporter. Points for your opponent. What the hell are points for your reporter? Don't take any straight.